Hi everyone, today we have something really great. Today we will create our own little script language for conditions in our dialog tree. If you remember, we had made this dialog tree. I've worked on it and highly increased efficiency of the tree. Because if you remember, when you needed to have conditions, if certain options are available for the player, then you had to make a condition node. But if for example one NPC had 4 options and 2 of them would be conditional, then you would have 3 condition nodes at least to create this scenario, and this will blow up the tree and make NPC dialogue trees in our game really complicated. To solve this issue, what I actually introduced was a condition field, which you can see here in front of each option. So each option can have a custom made condition if we want to. For example, we can say our NPC here, which is called Hans, is able to talk, and we could answer, fine, where am I? Do you have work for me? But do you have work for me should only be available if the character level is greater than 10 and if the quest is available, which basically means in our case we never have done the Hans quest. And now only this option is only visible if this is true, which after we finish the quest, because it's available, will be false. Then the option is not available anymore, or if the player already has accepted the quest, which is great. That's exactly what I want. But who parses this line of code and who understands it? I highly recommend you, if you want to do something like that, you implement Lua or something, because this is open source and highly tested. But 9 years ago, I actually developed my own compiler, and since I have my own compiler, why not leverage it? I take the opportunity to put my own compiler in the MMORPG and show you how you can develop your own compiler and your own scripting language. One disclaimer: my compiler is actually fully fledged, able to compile code with object-oriented structure. But in our MMORPG, we just have one-liner, so I scripted away in the virtual machine. So how does compilation of code like this works? It's typically a 2-step process to compile the code, and then it's 1 step or 2 steps to make it executable. The first step is taking this code and creating a token list out of it, so a more understandable structure than what we have here. This algorithm actually is quite emotional for me, because when I was very young, around about 14 years old, my father actually gave me the task to be able to do something like that. You get a console input, like a little formula, just like I marked here. Let me increase the text size. And you get it, some arbitrary person in a console application inputs this formula, and you have to print out the result. One key difficulty increase: you have to preserve operation precedence. What that means is everyone learns in very beginning in their school life that a multiplication is solved before an addition. So this is actually solved like we multiply 1 with 2, then this is 2, and then modulo basically is we count it as a multiplication now, then this is 1, and then you do the addition afterwards. And my father actually also wanted me to be able to do parentheses, I think they're called, and to allow multiple of them, and so on and so on. And with 14 years old, I never knew the algorithm completely, so I hacked something down which actually worked, but was quite inefficient. What I did when I was younger, I looked for parentheses and solved them first, and then I had operation precedence work the way that I searched for the highest precedence, in this case multiplication, solve them first and then the other ones, and always replace the result within the string. With which A doesn't work in our case, I will explain why, and B is very inefficient. And if you know the algorithm, which my father taught me after I showed him my messy result, it's quite easy to do actually, because the algorithm is quite sophisticated, but we will get to that. And as you can see, we also have a little virtual machine running. We can run the test when I run this short test here. I'm here, and this is the full complex formula. Then these outputs, sorry for going through my debug code. So then this outputs 4. Is that correct? Actually it is, because I made a crucial mistake here in the top. We have 3 modulo 4, which is actually 3, and then this formula looks like that, and then we have -1 + 2 + 3, which is 4, which the result is correct. And I wrote a bunch of tests to test all kind of compilations, and obviously we need to be able to do our quest.isAvailable and everything, function calls to in the virtual machine to functions we will later define in our game. And we have something like that. We want to give quest.isAvailable with tutorial quest as a parameter. Our virtual machine and our compilation and virtual machine execution should return this, because we created a mock for our game. This is where our game hooks in and says quest.isAvailable does this and that. It just returns a number with -1. So when we execute it and our code understands this, it returns a number with -1. -1 is also true. The reason why -1 is true, if you might ask, why do software engineers do not make 1 true? First of all, in most languages, everything non-zero is true, but -1 is actually really good because every bit is true in the integer, for example. When you have an integer with -1, then every bit is actually 1. So when you add 1 to it, then every bit will flip to 0 and you have some overflow happening there. But in case you're wondering why -1 is true, most likely. So I don't debug that now. We just run the test, and you see, since the result is a number and it's -1, that it actually has called it. And our mock framework also gives me the opportunity to say, to verify the mock, which basically says in this case, it got called with isAvailable with the parameter string tutorial quest and only once. And since the test is green, let me check, VM scope test, it is green. This is actually all true, which is great. Now, obviously, we want to have something like that. This is pretty much the example which I gave before. And what did we say? We say it returns true because the quest is available. And the character level, when we call it, will return number 11. So the virtual machine gets from our game that the character is level 11 and the quest is available. So this should be true. And since it's green at the bottom here, it's VM full character. You get the idea. It's true. And always when you do testing, also test the negative part. The quest is still available, but our character sadly is just level 9. And now the result should be 0, still a number, and it should be false in the interpretation, which also happens to be true here. So this is working, and we can leverage that really good in our game with the tree which I showed you. Which is great because game designers, or when we create NPCs, we can make this complex dialogue structures really easy. And it's like that. Our NPC says, "Hi, how are you?" And you can answer, "Fine, where am I?" And if you're capable of getting the quest, you can get a quest. And then you can answer fine, then you say fine, how are you? Then you can just continue because there's no option for you. And then he says fine, thanks for asking, and dialogue is done. Then you can talk to the NPC, can say where am I? Then he will tell you a little bit about the lore, which I cut it out here because I don't want to spoil too much for now. And later, which is your tutorial first quest, because Hans is the first NPC you will meet, you can get a quest and you can accept the quest and everything. That's the idea behind it. So now let's talk a little bit about the compiler. Like I said, there are multiple steps to do a successful compilation process. And let me show you what the compiler actually is capable of doing. We have here with commentary, and there you see this is actually a test from my scripting, where we can define classes with properties, with functions and everything, and have for loops, while loops, if loops and everything, and the second class in the same source code file, and it will actually compile it pretty well, and it will also give you line numbers and everything if you have some syntax error and everything. But since this is really complicated to write a really good virtual machine for that, and we don't need that, our virtual machine is the part that is not intelligent enough to do that for now. We could increase that. I'm fully capable of doing that, but I don't want to waste more time since I want to get the game going. And if we later want to or need that, then I can always go in there and make the virtual machine more intelligent. So we want to compile more likely than this. But I actually have a compiler test which compiles the complex structure and compares it to an AST tree. What is an AST tree? AST tree stands for Abstract Syntax Tree, and it's actually the end result of our compilation process. And it looks something like that. Let's say we have our is quest discovered or is available, doesn't matter, and quest is not finished and character level is greater than 10. This is a statement, and an AST tree for this statement looks like this. You have one operator AND and the other operator AND. Then you have the operator NOT. Then you have the function call for quest is finished. You have the function call for has discovered Hans, and then you have a check if the character level is greater than 10. And this is obviously a call to character AST function call character level with no parameters. That's actually a reason why you let a computer compile that and not a human do that. So this is what an AST tree looks like, and it could be more complicated. For example, we could have here AST class with properties, and then the properties have nodes like that. But it's actually a tree which is a syntax independent or with an abstract syntax, which shows the code compilation process. And our virtual machine can directly execute this tree, which is really simple because it starts at the top at the root node, which in this case is an operator with AND. So it needs to process left and right side. So we recursively call give me the result of the node for the left and right node, and for the right node it says, okay, it's a greater than operator. I need to it's a binary operator. I need to know what left and right result is. Then it calls AST function call. Okay, AST function call is a function call in our game. So our virtual machine will do that and will get the result, which is the level of the player. Let's say it's 11. Then AST number is a fixed number. It's a direct result. It will plug that in the operator, and the operator will report its result up for the root node. Same goes to the left. Does a function call, does not operator will is a unary operator, will get the result of the other function call, will negate the result, and it traverses back up, and at the end we get the result. And if you have more complex structures like classes, structs, functs, and everything, it works in a tree the same, but the virtual machine needs to do certain other things to fulfill that. But since we don't use that in our game, let's keep it a little bit simple here for now. Normally, you can do code optimization on this AST. So you can take this tree and you can do sophisticated mathematics and everything to optimize code with this tree. And this is actually what compilers do, at least to my knowledge. But doing code optimization here farly exceeds my knowledge, so we shouldn't go in there. But we could also compile this AST tree into bytecode, later have some virtual machine execute the bytecode, but we will skip this step and directly execute the AST tree, because we most likely will compile short lines like this, then we can compile them on runtime. So compilation takes less than a millisecond for this line of code, and then executing the same. So we are in a 1 millisecond window to compile and execute this little line. Then we don't need in our game that we compile it, optimize it, put it in a bytecode and for later, so that we can have pre-compiled execution. So, but how does compilation process works? First of all, you get the string, which is just a big string at the end or a file, and you need to split the string up into, which is often called token, and the process which does that is called lexer. So we have a lexer which basically takes a string and creates a bunch of tokens. And let me show that to you. So we have here lex, which is should be the only public function, where you give the source code and you get a bunch of tokens back. So let's actually check out what this does. And let's make a simple example for now. Let's take this one. It's -1 and true as string. It's VM number and string. This should be the one. We go inside and debug. Then we have here the steps. We do lex the source code, then we get a token list, then we pass the token list, and then we get the AST tree. The statement here is the AST tree for the statement. And then we have our virtual machine. We add the external calls the virtual machine can do to the virtual machine list, and then we execute the code. So let's check. Let's remember our code is -1 and true as a string. True as a string for our virtual machine is true. So we get 4 tokens back, which is first of all an operator token -1, and here it also says the operation precedence. which is 3, but it's actually not true because it's an unary operator, but that's some minor detail for now. Then we have the number 1, because -1 is actually in our solution an operator and a number. Then we have the next operator, which is and then we have a string token, which is true. So there's no logic done with those tokens. It's just like what is in the string, the most simplest way you can think of that. So let's take something extremely complicated, just to give you an understanding what it looks like. Let's take this complicated one. And here we have compile classes test. Oh, this is the wrong one. So, and there we get the tokens, 258 of them. We don't go through all of them. But first we have the reserved word class. Then we have an identifier, which in our case is the class name. Then we have the token, curly bracket open as a special token, and so on and so on. This is actually not hard to do, to get the tokens. To be honest, writing a compiler like this, every single step on its own, it's actually quite simple. So we split the source code, which is basically going through the source code left to right and read each char. And then we check, is it a special char? If that's the case, then we finish the previous token, because there could be an identifier or something before the special char, which is already saved in current token, but is actually not saved in our token list. So this basically takes this function finish previous token if needed, checks if current token is empty. If it's not empty, then it will add it to the tokens list. It's not doing more than that. It's very simple. So we go from left to right and we check each token or each character if it's special. And at the top, I have basically defined the full structure of our source code. So we have reserved words, which is function, class, string, number, object, void, new. You get the idea. If, while, and for, return. Those are all reserved words. Then we have tokens that we totally ignore. We don't care for them, which is basically white spaces and spaces and a carriage return, because we will just process new line like Unix. Then we have special tokens, which are brackets, semicolon, and everything. Then we have our operators, and we have escape sequences. What is a string quote, and yada yada yada. And basically we go from left to right, which is all we do. And we check, is it a special token? If that's the case, then we select special token. And special token is basically just adding a token with the character. So we check again, what is a special token? Oh, sorry. Special token is, for example, bracket. So sorry for jumping back and forth. If we have a special token, we save this token in the token list, and if there was a current token before that, we also save that. Then if something is ignored, then the thing is, if we find an empty space in our code, for example, we have something like 1 plus 2, then this space will indicate that this number is finished. So if this number would be in current token, we ignore the space fully, but we want to process the 1 in this case, which basically we do. If it is an operator, Then we have a special lex operator function, which is just checking if the operator is basically a two-char operator. We could have, for example, operators like plus plus. If you do something like I plus plus, then this is where our current pointer in the source code is looking at the plus, and we need to check if there's a second plus or something, if it's a two-character operator. What we do here, we check I is basically the next one, and we check first of all that we don't have an issue with that, and then we give a proper error when the source code has ended with plus, then something isn't right, because source code shouldn't end with an operator. And then we check if the second character is an operator, and if that's the case, then we add it as a two operator thing. So here's the issue. Single line comments are actually operators, because this is a division. This is two divisions behind each other, and this is a division with a star. So if we detect we have two operators, then we have this special case where it could be a single line comment or a multi-line comment. If it's a single line comment, we skip the source code till the next line, basically, and if it's a multi-line comment, we skip the source code till the end of the multi-line comment. Straightforward. So then we add the operator. If that's not the case, then we add the single operator, a simple plus or whatever. And otherwise, sorry, this is not right. Otherwise, we check if it's a new line. If it's a new line, then we do basically the same as ignore token, but we increase also the line number so that we know if we give out error messages where we are in the source code. And if we have a string token, then string quote, then we lex the string, which is basically read to the next string quote and check for escape sequences so that we can have string quotes in a string and everything, and save this token as a string token. And if none of those at the top apply, then we have like an identifier or a number, and then it will add this as a token. So we have the source code split. After that, let's go back to our simple example, numbers and string. Which we remember as -1 and n2 as a string. And our split source code looks like this. We have lexer tokens, it's a minus, it's 1, it's and it's true with quotes around it. And this just is basically splitting the source code in tokens. And now we do a check what each is in our token. Is it a reserved word? If that's the case, then it's a reserved word. First token is -1, so it's an operator token. Second token is a 1, if I remember correctly. We check, is it a char digit? So is it a number? And if it's a number, then it could be a longer number, and we have a dot as splitter, and this basically checks that only one dot is in your number. So if you write a number like 1.2.3, then this is not a valid number for us, obviously. And this just checks that and it validates it's a number, and then it adds it as a number token. Then our next token is and, so it's an operator again. You get the idea. And the last one is a string because it starts with a quote, then it's a string token, and we remove the quote. This is basically what this line is doing. So it starts one one ahead in the string, and it removes 2 because the first and the last character is removed, so the length is -2. That's how this works. And then we have those 4 tokens that we are working with. This is the lexing part. Now comes the more complicated part, which is basically taking this token and token list and create the AST out of it, which is called parser. So next thing we do is we get the token list, and I made a special function, parse inline statement, which is just this for parsing this one statement. So let's run that again and let's go through the algorithm. So first of all, we call parse statement and configure the parser. So we configure the tokens list, and we are currently at token 0. So what parsing does is actually creating this tree with keeping in mind all the special cases, which this parser can do classes and everything like I showed before, but those are not interesting for us, so I will skip over them because else this video is 10 hours long. But if you have any questions about the code and everything, I wrote the code, just give me a comment on YouTube, I will answer it, or join my Discord and talk with me. We can even call each other, and I'm more than happy to explain everything about this code to you that you will find. So first thing we have is -1, which starts with an operator. So when we have an operator, this whole check here is checking if the operator is a unary or a binary operator. And we have a unary operator because it's -1. Then it knows that it reads the operator minus. It says that the current node is the AST operator node with minus. And it says that it's only everything that comes afterwards is a statement for this minus. So the next thing afterwards, is the statement for this minus. So we go to parse single statement, which expects it to be a number or a string or a reserved keyword or a function call. Something like that in those lines. For us, it's a number or a string or a function call, because our virtual machine doesn't work with other things. So in this case, it's 1. So the next token is a number. So it returns AST number as its thing. And then we have passed our first 2 tokens. Minus, which passed as a parameter of the minus in the left node, the 1, and we have our first node, our first two nodes, which is minus as an operator and number 1 as the left part of it. And we add this to the node list. Then we go through for every other. We have the next thing is a binary operator, which is AND. And the interesting thing for the binary operator, since we can't pass the left side of the binary operator because we already have been through this, for now we just save the operator into the list of AST nodes for now. We build the tree later with the operator precedence in mind, if you remember the thing we called at the beginning. So we just add the node as AND as an operator to it, and then the next one is basically the string. So we go back to single statement, and it's a string. We add the string AST node. So first step is converting those tokens into nodes, which are currently for now mostly independent. The only thing that is not independent are unary operators. They already have on the left side the part of it that it is converting. So, and now comes the tricky part. So basically this just converts the token with this one special case into nodes, but there is no structure to it because this part doesn't know or doesn't work with the precedences of the statement. And then we have the tricky part in apply operator precedence. And before I go over it, if you want to mimic my 14-year-old myself, you can obviously pause the video and try it yourself. Feel free to load up your source code at GitHub. I will take a look at it because I'm really pumped to see what you guys come up with. If you want to get spoiled, then I will show you a very efficient algorithm to actually fix this or do this. There are just some simple rules if you know what you're doing. First of all, we need 2 stacks. Those stacks are last in, first out. So what we put in last on the stack is coming out of the stack first. And then we remember the last operator precedence that we had. Now comes the tricky part. If we have an operator, we will add the operator to the operator stack. And if we have a non-operator, then we add this not operator to the parameter stack. Which in simple case, if you have 1 plus 2 multiply with 3, then you have 3 parameter, next is operator, next parameter, next operator, next parameter. The tricky thing is we go the nodes from right to left. So we actually start with the last node and end on the most left one. So we start with count -1 and we end on 0. So we go from right to left. And there are some special cases. So the other function, so we build up those stacks as we go. And there are some cases where we need to process those 2 stacks and add the result as a parameter back to the stack, which is what this function process operator stack does. It basically gets the operator which got put last on the stack and gets 2 parameters. As long as there are 2 parameters available, it gets those 2 parameters and adds them as left and right to the operator. So we take the operator node and add the 2 parameters below it as parameters. And then what we do with the operator node, we add it back as a parameter for the next operator. And there's a special case which I ignore for now. We will talk about this special case later. But all this process operator stack does is goes through the list, gets the operator, gets 2 or 1 parameter if only one is available, adds them to the operator, adds this operator back as a parameter on top of the list, gets the next operator, gets those parameters again, adds them, and so on. And at the end, you only have 1 parameter, which is basically the tree that it has built for now. So there are special cases when we do process the stack. If open parentheses, then we process the stack fully. If the precedence of the last operator was lower than the precedence of the current operator. Let me explain that. Let's first of all check what precedences are available. I think it's in the operator token here. Let's take multiply. Multiply has the precedence 2 and addition has the precedence 3. Each operator that we support has a precedence. This precedence list is basically copy-paste from C# language. So multiply is 2, addition is 3. So let's say we have an example like 1 plus 2 multiplied with 3. Remember, we go from right to left. So when we reach the operator multiply, then this is basically max value, so it should never apply. So the first interesting thing is when we reach the plus. Then our stacks look like this. We have stack parameters, it is 3 and 2. And we have stack operators is multiply. And in our case, last precedence is 2 because multiply was 2. And our current operator precedence is 3, which in this case, OP precedence is 3, so this is true. What that means, that this stack gets processed. So we have as parameter 3 multiplied 2. This is the parameter. Then we add the plus again as operators as the loop goes on. And we add the precedence, we add the parameter 1. And at the end of the whole loop, we process the stack, obviously. So then this will be, the tree will look like, the last process will take this parameter as a parameter for plus and has this 2 operators. So if we have a tree structure, then at the end it will be like, this will show into multiply, which shows to 3 and 2. Forgot here. This also shows into 1. So at the end the tree will look like this, which is correct. Because when we process the tree, we say, okay, plus we need to get the result of this operator, which is 3 multiplied by 2. So this result is 6, and 6 plus 1 is 7. So result of 7, which is correct. That's all there is for this algorithm. So if we have another, for example, plus 2, then let's see if this works again. First we add 2 to parameters, then we add a plus to operators. Last precedence is 3. Then we go right more to the left, we add 3 as parameter, and then we come to multiply. Do we add multiply? Yes, because last precedence is 3, multiply has a precedence of 2, so last precedence is greater than the current precedence, so we process like nothing has happened. Then we add the operator again, and then we add the next parameter 2. Then we come to the operator plus, which in our case processes the stack, because plus last precedence, sorry, I didn't update this, multiply last precedence is 2, and the plus has a precedence of 3, so we process the stack, which creates a tree like this. It goes from here, it takes the operator multiply, adds 2 to it, and as second parameter adds 3 to it, and this is added as a parameter again, so this is 2 multiplied by 3, and this is processed. Then it gets the plus, so the next tree will look like this. Plus will have 2 multiplied by 3, which is basically this tree for, let's write it out, why not, which is 2, and this will go down, which is 3, and this has then the last operator 2. So, and this gets added to the as a parameter again. So next thing comes around, it adds the plus as an operator now, it adds the 1, and since we are at the end, we process again, this whole thing gets moved, and we have here plus with the 1, and the tree at the end will look like this. So plus 1 plus multiply and so on. One edge case, which is the edge case I told you we talk later about, is, for example, if you want to have something like equal. And let me go to the test, which shows the complex issue. The bug in my old language was if you have something like that. Because we processed and here with the plus we need to process this. But we shouldn't go over the close parentheses. We only go over the close parentheses if we hit the open parentheses. So let's check the algorithm again. With processor operator stack, the only thing we do, we have this parameter remove parentheses, and if remove parentheses is false, then it stops basically the operation. It pushes the parentheses back on the stack because it popped it here, but it stops the processing of the stack. And also good to know is if we find remove parentheses, we only remove 1. So when you have a formula like 1 2 multiply 2, even if this formula makes no sense, if we reach this open parentheses, the stack is only fulfilled. We only remove 1 parenthesis, so it stops after this parentheses. It will process this part, but it doesn't go over the second parentheses here, which is just the edge case scenario. And when you see where this function is used, when we go to get an open parentheses, we go over 1 for normal precedences of operator. We don't go over 1, and if we are at the end, we obviously want to process as far as we can. This should be true, false, and it should be fine, because every closed parenthesis should have an open parenthesis here, but whatever. So this way the language is a little bit more flexible. So if you forgot the last opening parentheses, it will accept that. And with this tree built, we wanted to check, right, if the tree at the end will look like this. So we take this formula, let's just execute the formula, and let's create a breakpoint here. I don't know why it's executed. Let's take a breakpoint here and let's check if the tree at the end will look like this. And the end obviously is here. So let's take a breakpoint here, and we go through the whole process. I think it's a good idea. So it's the first formula, so the first breakpoint hit is this formula. let's remove all those. Great, we are here, we have the nodes 1 plus 2 multiplied 3 plus 2 with straight formulas look like these nodes. And then we go through it. Like I said, we go right to left. So we start with the 2. We go, and it's not an operator, so we start at the parameter 2. Then next is the operator. Last precedence is max value because it's the first operator. So we save the precedence. From the plus is a 3. And it's a plus, right? Yes. From the plus it's a 3. We add this to the operator. Next is our next number, which is the 3. We just add the 3. Then again, we go to the multiply operator. Multiply operator has a higher precedence than the plus. A lower precedence. Multiply operator has a lower precedence than the plus. So we don't process the stack, we go on. And then we add the next number. In our case, it's the 2. And then we are at the operator plus again, which has a higher precedence. So we need to process the stack. We go through the stack, we get the operator, we get those 2 parameters. The first operator we get is the multiply, because like I said, it's LIFO, it's last in, first out. We get the 2 parameters, we add this back as a parameter, we get the next operator, which is plus, and we get the next 2 parameters, which is the multiplication and the 2. And we add this to the operator, add the operator back as a parameter. So we have, like we drawn before, plus with the multiplication with 2 multiplied 3 and the number 2. And we go back and process the rest. So we add the plus now as an operator, then we add the last number. We add the last number as parameter. We are basically done. We process the stack again, which is just our 2 parameters with the number 1 and the whole thing we already passed and the operator. And now we should see this tree structure like we have drawn, which we have. We start with a plus. We have here with number 1 on one side and with another plus on the other side, which has multiplication on one side with 2 and 3 as children and the 3 on the right side. And this is basically the AST tree for our formula, which is great. And this is how compilation works. And I have written some codes about this and that, and it executes well. It calculates that this actually is 1 at the end, and it checks with the equal parameter, and the equal parameter says it's true and gives us true, which is correct. Virtual machine side actually is quite easy, because we just execute the AST tree. So for each AST node that can happen in our tree, we write a small function which executes that. So let me go through that real fast. So we go through each node and we execute each node. Simple as that. Because we don't support classes, and for now in the virtual machine it's just statements like you saw. And we have a statement node. If it's a statement node, then we just want to return the statement. So we get from the statement node the statement and execute it. And return that. If it's an operator, then we want to execute the operator. And then I made 2 functions, one for unary operator, which is the case when the right side is null, then it's an unary operator. If right and left side of the node is filled, then it's a binary operator. So for binary operator, we basically execute the left and right part, and then we do our operator on left and right part, whatever that is. That's for operator. If it's a function call, then we do a function call. We support this add link scope where people can add their own functions. They have to define a scope, which is if you write, for example, quest.isAvailable, yada yada, then quest is the scope, this is the function name, and this is in this parameter list. This is how that works, and you just go through the executed with your scope. So you can add your quest scope with the little function you want to have, and you have to return VMvar for us to process it any further. That's our function. If it's a number, if it's an AST number, we just return the number as VMvar, and if it's a string, we return the string as VMvar. And that's basically it. We go through that, and since when we have an operator, we process left and right, which basically goes back to here, process the left part, the right part, and then combines the result with the operator. And everything magical is happening in var-mvar. var-mvar could be of type number or string. And if it's a string, then value string is interesting. If it's a number, then value number is interesting. This is a small cast function, so we can actually cast string into numbers and numbers into strings. So when it's a string, and when we want to cast to string, then we say value number to string. If you cast accidentally a string into a string, then we just return a clone version of it. But if so, you can have just put in a number and want to cast it to string, then we just do value number to string and return it as a string. The other way around is a little bit more complicated because we need to pass the string as a number, and let's hope that there is actually a number in the string, and then we return the result as a VMvar number. That's how casting works for us. Then we have a small helper function who defines what is true and what is not. So if the string is empty or it is false in any kind of written way, so we lower it, so you can have a big F, a big A, or whatever, we ignore that. So lowercase false or empty or null, then this is false. Every other case for a string is true. For numbers, if the number is a 0, then it's false. Every other number is true. That's how simple we work with that. The other way is set function. If you want to set a bool to a string, then it's true or false. And if it's a number, then it's -1 or 0. Then we have a small clone function, so we can clone this VMvar because I was scared that I modify too many variables, and so I cloned everything, which is very inefficient, but it's okay for us. And then we have a bunch of operator overloaded and implemented. So we have the not operator, which is really easy. We get a VMvar, we clone it, and the result basically is set bool negative get bool of the VMvar. That's how our not operator works, and it returns the result. And if we look through the operators minus, we cast everything that comes into a number because this is basically unary operator, unary minus, so -1. For example, we cast it to a number. Remember, if it is a number, then we just get a clone version. And then we say value number is equal to minus value number, and that's how we implement this. Here, and we have and for A and B, then we clone A, write in the result in the clone of A the get bool of A and B. Simple as that. The reason why we clone it here, that's actually quite interesting, is to get the type. I could here do new VMvar, and if I do new VMvar, then the type is always a number because that's our default. But when I clone it, I actually clone the type of the first variable. So when we do an AND with a number first, then the result is actually a number. And if we do an AND with a string first, here true and minus 1, then the result is a string. That's how I preserve it. I clone the first variable, and setBool is checking the type. So then we have OR, we have true, false, equals operator, plus unary operator, minus unary. I don't want to go through all of them because they're all stupid easy. If we have greater than, we cast to two numbers and we return if it's greater or lower than. We return a bool here, which actually is not what we want. We want to return a VMVar. So we have a little bug, which is fixed now. We want to return a VMVar. C# actually knows how to convert a bool to a VMVar because I have operators overwritten for that. Because here we have implicit cast operators to bool and from bool. So when I return a bool and I say it's a VMVar, then it will convert it into a VMVar for us implicit, which is in this case always a number, but that's fine. So, and we can run all sort of things now. And it works. That's how we implemented our own script language. Basically, for conditions, we have XOR everything that we need, and we have those functions, if you remember, that you can override, and you can just add the scope to the VM, and that's what our game will do. Our game will add a character scope and will return the actual character level of the player, and that's how this is working. I hope you have a blast. Like I definitely had a blast writing this, because that's actually something I really love to do, writing my own compilers. Have a good day, have a good weekend, and like always, I really want to thank my Patreon, Julian, for supporting this project. Bye.